Okay, let's talk about the chapter 13.3, geometric sequences and the geometric series. Last section, we already discussed the arithmetic sequence. Arithmetic sequence. Arithmetic sequence means that this difference is a constant. For example, you have a 1, 2, 3, 4, 5. So the difference, the next term minus the current term is always a 1. Or you have a 1, 0, -1, -2, -3. This is -1. Or you can just get whatever, like 1, 3 halves, 5 halves. No, every time plus 1 half. It's a 2. 5 halves, 3, 7 halves, yes, 7 halves, 4 something. The difference is 1 half. So whatever. Or you can get like 1, 1, 1, 1, 1. The difference is 0. You can have positive difference, negative difference, and 0. So the recursive formula is an minus 1 is a constant. So this is arithmetic. Arithmetic sequence. Arithmetic sequence, remember that the general term an is a initial term, first term, plus d times n minus 1. And the sum a1 plus an is equal to first term plus the last term. So you see, it's from 1 to n. There are n terms, and divided by 2. Okay, so this is a sum. Sum of n terms. This is a general term. Okay, it's very, very important. Arithmetic sequence is one of the fundamental sequence. In this section, we talk about a geometric sequence. What is a geometric sequence? Here is the difference is constant. Then geometric sequence means the quotient is a constant. The quotient is a constant. In other words, you have such a thing. So first, let's see the definition. So a geometric sequence may be defined recursively. This is recursive. The current term depends on the previous terms. This is recursive. Recursively as, so you have the starting point. A1 is equal to A, and then your relation is that an over an minus 1 is equal to r. Okay? Sometimes you don't want the ratio, you don't like the quotient. Or you have a1 is equal to a, and an is r times an minus 1. Either way. If you prefer the ratio, you get an over an minus 1 is equal to r. Or you get an equal to r times an minus 1. And this r is called the common ratio. I'm sorry, ratio. Like d is called the common difference. The same thing. That's geometric. If we write a few terms, let's see what they are. The first term is a. It's a definition. The first term is a. And second term, you have a and multiplied by r. And third term, you have the second term and multiply it by r. And third term, you have a first, second, third. Fourth term, you have a third term, you multiply it by r. This every time just multiply by r, multiply by r. This is a geometric series. Let's see the example. So for example, assume we have this sequence 2, 6, 18, 54, 162. For this sequence, let's check the 6 over 2, 3. 18 over 6, 3. 54 over 18, computed 3. 162 over 54, yeah, it's also 3. So based on the given information, we see that all the ratios, the next term over current term, all the ratios, we see the ratio, all the ratios are equal to 3. It's a constant, so it is a geometric sequence. It is a geometric sequence. Possibly from the future data, this pattern is broken, but up to the given in data, it is a geometric, right? With what? With the initial geometric series is sequence. Geometric sequence is determined by two quantities. One is the initial value, the first value. The other one is the common ratio. So with the A1 equal to 2, the initial value must be 2. The common ratio equal to 3. So in order to determine a geometric sequence, you need starting point, you need your multiple, right? You need starting point and the multiple. Okay, so let's check next example. Show that the following sequence is geometric. Sequence is Sn or equal to 2 to negative n, 2 to negative n. Find the first term and the common ratio. And the common ratio. Okay, so now we have the general term. If we have the general term, we cannot just examine a few examples and say it is a geometric. We have to really follow the step. The essential property is that they have the common ratio. Common ratio is Sn over Sn minus 1. Sn over Sn minus 1. Okay, so what is Sn? Sn is a 2 to negative n. Sn minus 1 means in the Sn formula, you replace n by n minus 1. And don't forget parentheses. Whenever you replace a simple symbol by a complex symbol, you put a parenthesis to be on the safe side. Okay, so it's a 2 to negative n over 2 to negative n minus 1. You remove this parenthesis, it becomes 2 to negative n and then plus 1. 2 to negative n, 2 to negative n, they cancelled. You get a 1. Denominator still have a copy of 2 here. It's from this 1. It's 1/2. The ratio is fixed. Sn over Sn minus 1 has a fixed ratio. So it is geometric. For sure, it is geometric. And for the geometric sequence, it is a common ratio. 1/2 is a common ratio. What is a first term? First term just means you evaluate n at 1. You let n be 1, you get 2 to negative 1. 2 to negative 1 is 1/2. The ratio is 1/2. This 1/2. This give you the ratio. Okay. So in order to determine a geometric sequence, you only examine this. That is a property, but in order to determine to write down a geometric sequence, you need the starting point. Like you say, every time I just double what I have, but you have to know what is your starting point. You start from 1 or you start from a million, right? So double it, that's an essential property. But 1 or million, that's your starting point. You start from San Juan or you start from Mayagüez. Okay. Determine a sequence. So we have this sequence Tn is 3 times 4 to n. Okay. We want to know if it is a geometric or not, a geometric sequence or not. So you just examine. In order to determine a geometric sequence, you only examine Tn over Tn minus 1. Tn 3 times 4 to n. Tn minus 1, 3 times 4 to n minus 1. Whenever you see n, you write n minus 1. 3 cancelled. 4 to n cancelled. And denominator you still have, you see here, this is a 4 to n minus 1. The denominator has n minus 1. N is already cancelled. 1 over 4 to negative 1 is 4. 4 to negative 1, this is 1 over 4. 1 over 1 over 4 is 4. Right? Okay, so it is a geometric. So the common ratio is 4. And let's check the first term. The first term is T1. 3 times 4 is 12. The ratio is 4. The ratio is 4. Okay? Okay, so we have a few examples about the determination of a geometric sequence. And geometric sequence, we start from the recursive formula. Now let's see the general term, a formula for the geometric sequence. Remember that right after the definition of a geometric sequence, we have something like this. We had this sequence. So the first term, let's see the pattern. First term, A. Second term, AR. Third term, AR squared. Squared. Fourth term, AR cubed. So in all the sequence, all the terms in the sequence have A. So if we have AN, it will have affect A. Then when you have fourth term, n is 4, you have 3. N is 3, you have 2. N is 2, you have 1. N is 1, you have 0. R to 0 is 1. So you have R to n minus 1. So every time you shift to n minus 1. Okay, so this is observation. Actually, this is also true for the general stuff. So the theorem says the nth term of a geometric sequence nth term of geometric sequence. So for a geometric sequence an whose first term is a1 and whose common ratio is R, then the nth term is determined by an is, you see, A is a1, R2, n minus 1. So the nth term of a geometric sequence is initial term times common ratio to the power n minus 1. And of course here we assume this common ratio is not 0. Common ratio is never 0. Okay, so this is the general term. The general term. With this general term formula, let's do the following example. Find the nth term of the geometric sequence 10, 9, 81 over 10, and 729 over 100, and so on. So first of all, we already assume it's a geometric sequence. It's a geometric sequence. In order to determine the nth term, we need the initial term, the first term, and the common ratio. What is the common ratio? Next term over current term. So the A1 is 10. R is 9 over 10. Next term over current term. You can use whatever pair. You can use 81 over 10 over 9. You see here, 81 over 10 over 9. You cancel 9 from the 81. It's also 9 over 10. The same thing. There's no difference if it is a geometric sequence. Okay, you have a initial term, common ratio. Then an is initial term times r to n minus 1. So it's 10 times 9 over 10 to power n minus 1. Okay. After you get the general term, nth term, find the ninth term. The ninth term, of course, is just A9. A9 is 10 times 9 over 10 to 9 minus 1. Be careful, it's not to 9th power, it's to 8th power. 8th power. See? Find a recursive formula. Recursive. Recursive form. What is recursive formula? Recursive formula means you determine the first term and the next term over the current term is equal to the constant ratio, or the next term is the common ratio times of the current term. So this is a recursive formula. You can either write it in the product or write it in the quotient. Okay. Okay. So now we have a bunch of numbers, geometric sequence. Sequence means you just have numbers. They are listed one by one. And when you have numbers, either you do addition, subtraction, multiplication, or division. The division, you know that the division is always a common ratio, pairwise. And the sum, let's see what is the sum of a geometric sequence. Before we can get the formula, let's check a few computation. Let's see, if you have 1 minus r times 1 plus r, so you do the computation, 1 plus r minus r squared, it's 1 minus r squared. And if you have 1 minus r, 1 plus r squared, 1 times all the terms, so it's 1r squared. Negative r times all the term is a minus r squared minus r cubed. So you see here, I write this way so that you can see the middle term, they always cancel, so you get a 1 minus r cubed. If you follow this pattern, you see 1 times all the terms. Negative r times all the terms, it's negative, so it's negative r times 1 is negative r. Negative r times r is negative r squared. Negative r times r cubed. R squared is negative r cubed. Negative r times r cubed is negative r to 4. They always, the middle term always cancelled. So here it's r cubed, then the final thing will be r to 4. So in general, if we have negative 1 minus r times 1 plus r squared, r cubed, r4, r5, up to rn minus 1, like this, it is always equal to 1 minus r2, here's 3, 4, n minus 1 plus 1. 1 minus r to n. So this is a general formula. So we're going to use this formula to find the sum of a geometric sequence. Okay, so this formula sometimes is written like this: 1 plus r squared up to plus r to n minus 1 is equal to 1 minus r to n over 1 minus r. I just divide this by this 1 minus r. Either way. Okay? Okay, now let's see, how do we add the first n terms of a geometric sequence? First, a. Second, ar. Let's label. First, second. Third, ar squared. Ar squared. Fourth, ar cubed. Nth, remember we know what nth, ar n minus 1. We want to add the first n terms from the geometric sequence. They all have common factor a. After we factor out a, we get a 1 r squared up to r to n minus 1. Check here, it's exactly this left hand side. It's exactly left-hand side. So we apply the formula. We get what we want. The sum of the first n terms of a geometric sequence. Okay, so theorem. Sum of the first n terms of a geometric sequence. The sum Sn, we write Sn. Sn is A1 times R. Sometimes I like to write A, just the initial term. They like to use A1. A1 times R to n minus 1. This is the sum of first n terms. N terms stops at n minus 1. It is equal to A1, 1 minus R to n over 1 minus R. Okay. And in this part, let's see. When we do the division, of course, the denominator is not 0. So this formula works for r is not equal to 1. And in the definition of geometric sequence, our r, the common ratio, is not 0. So this formula works for r is not 1, r is not 0. If r is 1, it's trivial. What does it mean r is a 1? R is a 1. It's constant. An is an minus 1. R is a 1, you just have a1, 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 all the sequences. Then you add them. You just have n copies of a1, so n times a1. It's nothing to discuss. There's nothing to discuss. So even though we exclude the case r equal to 1, but we actually don't lose many cases. We just lose a trivial case. Okay, so that's the partial the sum of first n terms of a geometric sequence. In this formula, again, we need the first term. We need the common ratio. So in order to get the sum, you need the first term, you need the common ratio. Okay, so example. Find the sum Sn of the first n terms of the sequence one half to n. That is find 1/2, 1/4, 1/8 n term. So n is 1, you get 1/2. N is 2, you get 1/2 squared. N is 3, you get 1/2 cubed. N is n, you get 1/2 to n. So that's exactly n terms. N terms 1, 2, 3, 4 up to n. Okay, so we're looking for the sum of them. Okay, so we have a sequence. In this problem, they never mention it is a geometric sequence. We have no idea at this moment. So we have to first make sure it is a geometric sequence. So how do we know it is a geometric sequence? Let an be 1/2 to n. Then an over an minus 1 is 1/2 to n over 1/2 to n minus 1. It is just 1/2. So it is a geometric sequence. 1/2 is a common ratio. So an is geometric. And a1 means 1n is equal to 1. a1 is 1/2. So ratio is 1/2. The initial term is 1/2. Then the sum Sn. The sum is initial term 1 minus r to n, 1 minus r. I copied the formula here again. So initial term 1/2. 1 minus r, 1 minus 1/2. 1 minus 1 r to n. You see, here we have a lot of 1/2, but you have to know what is the meaning of 1/2. So 1 minus 1/2 is 1/2. Clearly, you cancel 1/2 from numerator and denominator, so you only have 1 minus 1/2 to nth power. Okay? So that's the sum of the first n terms of a geometric sequence. Okay, so that's if you only consider finite sum, just add first 100 terms, add first a million terms. You can always do this. There's no restriction. Apply the formula, get the answer. Let n be the required value. And sometimes we don't just want to add a few terms. We want to add infinitely many terms. A lot of terms. That a lot means infinity. In this case, we have so-called series. Series is an infinite sum. Okay, so this a1 plus a1r plus a1r squared, a1r cubed. If we add all the terms of a geometric sequence together, this is called an infinite geometric series. You have infinite, it's a series. You have a finite, it's a sum. And is denoted by the following thing. We don't want to always write this long form. We write short form. It's a series. We'll do addition, sigma. The formula, you always have a1. You have r. R, you have the index. The power. Every time it increases 1 by 1 by 1. So when you have the case term, nth term, the nth term has a power n minus 1. N is from 1 to infinity. This symbol just means this long sum. It does not give you the value. It just gives you a short writing, a short form. A short form of it, not a value. It's just a formal writing. Okay? So check here. When we have sigma a n, n from 1 to 3, this means the sigma notation. You first let n be 1, a1, and then you jump to 2. The n is always integer. You jump to 2, and you jump to 3, a1, a2, a3. And then you do addition, sigma, sum. addition. And this part is from 1 to 2 to 3 to 4 to infinity. So you have the infinite sum. It's a series. Okay? So when you have this infinite sum, for example, this part, you have Sn. You add first n terms, add first 100 terms, add first million terms, add first billion terms. You will add more and more terms. If Sn approaches a number L as n approaches infinity, we say the geometric series converges to L. Actually, the same thing. Converge, approach, this is like the formal technical word. This is like a oral word. Okay, and we write the sum, the infinite series is equal to this number. Otherwise, it diverges. Otherwise means if Sn does not approach to any number as n approaching infinity. If Sn does not approach any number as n approaching infinity, we say the geometric series diverges. Converges means when you have a number. Diverges means when you do not have a number. Okay, so let's check. That's a word. Sn. Remember, Sn is a1 1 minus r to n over 1 minus r. We only talk about the geometric series. This is the sum of the first n terms. And this sum, only this part depends on n. Other part does not depend on n. N will approach infinity. If you have a constant, it's always a constant. So let's do the multiplication. A1 times 1, A1 times r to n. Well, let's see the pattern. Assume if r is 2, if r is equal to 2. If r is equal to 2, r to n is 2 to n. 2 to n will go to infinity. 2 to n will be definitely go to infinity, right? So 1 minus 2 is negative 1, so it gives you the plus. That's not a problem. For whatever a1 times infinity is infinity, so this part will go to infinity. Go to infinity, of course, it does not approach any number, right? If r is a 1/2, then r to n is a 1/2 to n. 1/2 to n, you check. 1/2 squared is 1 over 4. 1/2 cubed is 1 over 8. 1/2 to 4 is 1 over 16. So it becomes smaller and smaller and smaller. So technically, it approaches 0. Right? Whenever you have this number, ops value less than 1, then you take power, high power, you shrink it. You shrink this value, reduce the value. So a1 r to n 1 minus r, this part approaches 0, times a1, it also approaches 0. It does approach a number. Because this is constant, that's why we leave it here. We don't discuss it. It's constant. It does not depend on r. Only this part, when r is 1/2, this will approach 0. So this gives us the universal classification. And here we only choose a positive number. Let's try if we choose a negative number. It's here. For example, we choose -1, the simplest one. If we let's choose -2, not -1 is. If we choose -2, you have r to n is -2 to n. -2 to n has some problem. Sometimes it's positive, sometimes it's negative. So when n is 2, you have a 4. -2 squared is 4. n is a 6, you have a 8. n is a not 6, it's not 8. n is a 2, yeah. No. And 2, 3, 4. 4 is a 16. Is already 16. And when n is a 1, it's -2. n is a 3, it's -8. So it becomes a positive, negative, positive, negative, positive, negative. If you always have positive, negative, it does not approach any number. Because it's a positive, negative, but it increases further. It go here, 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 like this way. Go up and down, and this wave becomes bigger and bigger. So it does not approach any number. So it diverges. And when r is -1/2, it also plus or minus, but this is like down. They approach 0. It becomes smaller and smaller, negatively smaller and smaller, so it also converges. Okay, so these two negative situations are different. So to summarize this discussion, we have our theorem. If ops value of a common ratio is less than 1, the infinite geometric series converges. Its sum is it's only the first term. This term will disappear. You see here, this part will disappear. Okay. So for the infinite geometric series, the series converges only when the common ratio has smaller absolute value. Absolute value of the common ratio is less than 1. In that case, we can find its sum. So for example, we have the geometric series 2, 2/3, -1, and from 1 to infinity. A1, R, n-1. This is exactly a geometric series. And, right? Geometric series. A number, base, n-1. Common number, a fixed number, base, n-1. So the coefficient is A1. R is common ratio. N is from 1 to infinity. Then it is equal to initial term over 1 minus R. So initial term is 2. R is 2/3. 6. So this infinite sum is equal to 6. Okay, so that's the case. So whenever you write it like AR n minus 1, AR n minus 1, then it is A over 1 minus R. Now let's show that the repeating decimal the repeating decimal 0.999999, this number equals 1. Why? Remember that repeating decimal 1/3 is a repeating decimal, 0.333. You add 3 of them, the left hand side it becomes 3 copies of 1/3 is 1. Right hand side is this, but still it looks like we lose something on the right hand side, but you do have the equality. How? Of course we cannot go through this way. We are going to go through our geometric series way. We're going through the geometric series way. This repeating decimal 0.9999 can be written as a 0.9, the first 9, 0.09, the second 9, and 0.009, the third 9. So every time you get one 9 and you get the proper zeros, you will have this series, the infinite sum. Whenever you have an infinite sum, is always called a series. Okay, and then here let's say A1 is 0.9, A2 is 0.09, A3 is 0.009. So how do you determine AN will be 0.0000? Total their n zeros and put a 9. In other words, this is 9 over 10. This is 9 over 100, 10 squared. This is 9 over 1,000, 10 cubed. Then this is 9 over 10 to n in the general way. See, A1 is 10, A2 20, A3 30, AN, they're n zeros. Okay. And with this, you can see the AN over AN minus 1. AN is a 9 over 10 to n. AN minus 1, 9 over 10 to n minus 1. You check it, the ratio is 1 over 10. It is a geometric series. The ratio has absolute value less than 1. So the geometric series will converge to its value. What is the value? Right? This one. That's A1, A2, A3, A4. You add them together. It is also equal to the initial term over 1 minus r. Initial term, this is initial term, 0.9. Initial common ratio, 1 over 10. 1 over 10 is 0.1. 1 over 10 is 0.1. So 0.9, 1 minus 1 over 0.9. 0.1 is 0.9. See, we do have our repeating decimal equal to 1. So in this direct examination, if you have repeating decimals, you don't lose anything. If you stop in whatever position, you will definitely lose something. Okay, so this is the discussion about geometric sequence and the geometric series. In the rest of the part, there's some discussion about the technically issue about the interest theory, compounded interest theory. So there, I'm going to briefly discuss it. I'm not going to discuss it in detail. So what is compounded interest? For example, you have $1,000. You're going to save it, put it in the bank. So the rate, the interest rate is R. It means 1 year, after 1 year, you will get interest rate. So after 1 year per year, after 1 year, you will have interest $1,000 times R after 1 year. And if you do not withdraw it, you will keep this $1,000 times R. This is interest, then plus your principal. So together, this moment, you have such amount of money in the bank, and the bank will automatically save it with the same condition. So the interest rate is still R. So you will have interest rate R. And after another year, after 1 year, after another year, you will have, you see, the principal becomes this. This is 1,000 times 1 plus R, factor out 1,000, 1 plus R. So you have a 1,000, 1 plus R. This is your principal times the interest rate R. And after 2 years, after 1 year, after 2 years, your principal is this, and your interest is this. Common term, you factor it out, it is equal to 1,000, 1 plus R square. This is 1, this is R, it's R square. So you can see that the amount of the money you get after the what did it mean? After several years, it is actually a geometric series. So this is quantity after 1 year. This is quantity after 2 years. So after n years, you will have money. Your principal times 1 plus R to n. So that's a like compounded interest. Compounded interest means when you have interest earned from the previous year, it is put in the principal in the principal, and then it will be considered when you have the interest. It's not like $1,000 is always the principal. This interest that is saved in separately. No. Okay. So this is some. I am not going to discuss in detail, but some. It is the compounded principal. Okay. Okay, we stop here. And in the section 13.3, you don't need to worry about this compounded interest. We don't discuss it. Assume we don't discuss it. You only need to know what? You need to know a few things. Let's check what you need to know. You need to know the definition. What is a geometric sequence? This is important. The definition. Okay, and second, this is the second page. I'm going to put it here and you check it. Second page, third page. On third page, there's a nth term formula. Nth term formula, very important. Hold on a second, let me see. Okay, and this is the fourth page. Let me quickly show it. My video limit will reach. And this part we have the sum for the first n terms. Sixth page. 7. The theorem, the geometric series is important. 8. And this example is important. We will see some similar problem in the exam. And 9. Okay, we stop.